We will now continue with our discussion on thermodynamics with a brief discussion on heat capacity and specific heat. What is the distinction between these two terms? What is specific heat? Specific amount of heat that achieves something very specific. Now, what is that? Specific heat of a substance is the amount of heat needed to raise the temperature of 1 kilogram of a substance by 1 Kelvin. Now remember, raising the temperature by 1 Kelvin and raising the temperature by 1 degree Celsius are exactly the same, because intervals measured in degrees Celsius and Kelvin are the same. So what is the definition of specific heat of a material? The amount of heat that is required to raise the temperature of 1 kilogram of a substance by 1 Kelvin is called the specific heat of that substance. Now, it means different substances requires different amounts of heat so that 1 kilogram of that substance may be raised by 1 Kelvin. Now, what is the unit for measuring specific heat? It is measured in joules per kilogram per Kelvin. The amount of heat required to raise the temperature of 1 kilogram of the substance by 1 Kelvin. And we will represent specific heat by the lowercase letter c. All right? 4,180 joules of heat energy is required to raise the temperature of 1 kilogram of water by 1 Kelvin. So what is the specific heat of water? The specific heat of water is 4,180 joules per kilogram per Kelvin. 1 kilogram of water requires 4,180 joules of heat energy to raise its temperature by 1 Kelvin. It's a tremendous amount of heat energy. Water has one of the highest specific heats for many materials. Now, specific heat of water therefore is 4,180 joules per kilogram per Kelvin. On the other hand, look at this. Copper, only 390 joules of energy are required to raise the temperature of 1 kilogram of copper by 1 Kelvin. So, what is the specific heat of copper? 1 kilogram of copper requires 390 joules to raise its temperature by 1 Kelvin. Means the specific heat of copper is 390 joules per kilogram per Kelvin. You can see the big difference between the specific heat of water and the specific heat of copper. You know, why is copper a better material for making cooking utensils? Have you seen that some good cooking utensils have copper bottom? Why? Because a small amount of heat will increase its temperature by a large amount. So you can increase the temperature very quickly if you use copper. The quantity of heat Q required to raise the temperature of m kilogram of a substance from an initial temperature theta1 to a final temperature theta2. Can you tell me what will that be? If the specific heat is a measure of the amount of heat required to raise the temperature of 1 kilogram of the substance by 1 Kelvin, what will be the amount of heat you need to raise the temperature of m kilogram of a substance from an initial temperature of theta1 to a final temperature of theta2? What do? Multiply the specific heat by the mass and then the change in temperature. the quantity of heat Q equal to mc delta theta. It's very simple to understand because C is a measure of heat needed to raise 1 kilogram by 1 Kelvin. So if you multiply C by m and the change in temperature, delta theta is the change in temperature, that is theta 2 minus theta 1. Now remember, this is the lowercase c, not the uppercase c, the specific heat. The quantity of heat required to raise the temperature of m kilogram of a substance from an initial temperature theta 1 to a final temperature theta 2 is Q equal to mc delta theta, mass times specific heat times the change in temperature. You should be very familiar with it. We're going to use that to solve problems as we move on. Alright, where delta theta is theta 2 minus theta 1. Alright, let's now talk about heat capacity. What is the distinction between specific heat and heat capacity? Remember, specific heat means the amount of heat needed to raise 1 kilogram of the substance by 1 Kelvin. If you want to increase the temperature of m kilogram of a substance by 1 Kelvin, in other words, the whole mass of a substance by 1 Kelvin, that amount of heat is called heat capacity. Heat capacity is measured in joules per Kelvin, and you represent that by the uppercase C. So distinguish between the lowercase c, which is the specific heat, and the uppercase C, which is the heat capacity. Now, can you give me a relation between those two? The lowercase c is the amount of heat per kilogram per Kelvin. The uppercase C is the amount of heat per Kelvin, the amount of heat you need to raise the temperature of the whole object, m kilogram of the object by 1 Kelvin. So if you multiply the mass of the object by the specific heat, you get the heat capacity. If m is the mass of an object, then the heat capacity of that object is C, uppercase C, equal to mass times lowercase c. Heat capacity equal to mass multiplied by specific heat. We will need that also as we move on. Now, another term we have discussed so far now, specific heat, heat capacity. Now, what is the meaning of molar heat capacity? I think the term itself is very suggestive what it means. Molar heat capacity, the amount of heat required to raise the temperature of 1 mole of a substance by 1 Kelvin. Now remember, mole is the basic unit in which you measure the amount of substance. Is that right? And 1 mole is numerically equal to the molecular weight in grams. The molecular weight of hydrogen is 2. Therefore, the molar mass, 1 mole of hydrogen has a mass of 2 grams, right? 1 mole of oxygen has a mass of 32 grams, and so on. So, the amount of heat that is needed to raise the temperature of 1 mole of a substance by 1 Kelvin is called the molar heat capacity, and we write it with uppercase C sub m. C sub m is the molar heat capacity. And what is the unit for measuring molar heat capacity? Joules per mole per Kelvin. Alright. If m is the molar mass of the substance, alright, let me see if you understood this. If m is the mass is the molar mass of a substance, and C is the specific heat of that substance. What is the relation between specific heat, molar mass, and the molar heat capacity? Well, specific heat is the amount of heat needed to raise the temperature of 1 kilogram by 1 Kelvin. Molar heat capacity is the amount of heat needed to raise the temperature of 1 mole of a substance by 1 Kelvin. So if you multiply the specific heat by the molar mass, you get the molar heat capacity. So molar heat capacity is molar mass multiplied by the specific heat. Alright, take note of these. We will be using this as we move on. Since water is H2O, its molar mass is 2, that is the molar mass of hydrogen. Now, the oxygen, the one water molecule is made up of 2 hydrogens and 1 oxygen. 2 hydrogens is 2, and 1 oxygen, the atomic weight of oxygen is 16. So 2 plus 16 is 18 grams of water is 1 mole. The mass of 1 mole of water is 18 gram, which is 0.018 kilogram. So tell me, what is the molar mass of water? This is the molar mass of water. Alright? So, can you therefore calculate the molar heat capacity for water? Now, what is the specific heat of water? We talked about it a while ago. 4,180 joules per kilogram per Kelvin is the specific heat of water. And the molar mass of water is 0.018 kilogram. Can you calculate the molar heat capacity for water? Molar heat capacity is molar mass multiplied by specific heat. Therefore, molar heat capacity for water is its molar mass 0.018 kilogram times its specific heat, that is 75.2 joules per mole per Kelvin. 1 mole of water requires 75.2 joules of heat energy to increase its temperature by 1 Kelvin. Alright, specific heat and molar heat capacity, you must be familiar with some of the common values of some common materials. I have given that in this table. Now here I have the specific heat and the molar heat capacity of some common materials like aluminum, alcohol, copper, glass, iron, and so on. You can see the heat capacity, the specific heat of aluminum is 900 joules per kilogram per Kelvin. You can see which of these substances has the greatest specific heat. It is water. That's right. Now, alcohol has a specific heat of 2,400 joules per kilogram per Kelvin. These values are useful when we want to solve problems.